Modern astronomical telescope shown here was invented in 1610 by Galileo. It was a small telescope, the aperture of about 2 inches. You look through this end of the telescope down here. So the aperture was shown up here, that's the diameter, 2 inches up there. 2 inches is about 5 centimeters. So what we'd like to do is use this telescope and ask the following question. How sharp were things when you looked through this telescope? What did it look like? And to do that, we've got to be able to use the formula for the diffraction limit, for the official sharpness of the telescope. So let's do that. Let's use that equation. We're looking here at the telescope, but here's a famous painting of the time that shows Galileo. He's the guy with the red beard up here. Showing off his telescope to the ruler of Venice, who's looking through the telescope. And what he's doing is he's looking out to sea. Venice is, of course, a port town, and they were constantly concerned about whether there were enemies coming by ship to attack them. And the telescope has this terrific ability to let you see something that's so far away your eye can't show it. We'd like to find out how sharp the telescope would be. Now, I better give you a warning here. We're going to be finding the official theoretical resolution of this telescope. It could very well be, we'll find out in just a minute, it could very well be that this resolution is not as good as the resolution that the blurring of the atmosphere gives us. Or maybe it's better. We'll find out, and we can judge that once we've done this. So let's go ahead and look at how you have to solve this problem. Here's the formula that we use. Diffraction limit, shown by dl, which means that's the size of the sharpest thing that you can see, is given by 2.5 10 to the fifth, and the units of this are arc seconds, times lambda divided by d. Lambda, of course, is the wavelength of the light you're using, and in this situation we're going to assume that lambda is equal to, we're going to assume that it's equal to 580 nanometers. Okay? And D, of course, stands for the aperture of the telescope. We're going to assume that D is 5 centimeters. And this equation is correct if both of these units are given in meters. That is, lambda is in meters, and D is in meters. So 5 centimeters, that's easy. In meters, that's going to be 5 times 10 to the minus 2 meters. 580 nanometers is 580 times 10 to the minus 9 meters. So let's solve the problem. Diffraction limit is going to be equal to 2.5 times 10 to the fifth arc seconds. This will be 5.8 times 10 to the minus 7 meters. This is in units of arc seconds. And we're going to be dividing by 5 times 10 to the minus 2 meters for the diameter of the telescope. And this is not a bad number to divide. 5.8 divided by 5, 10 to the minus 7 divided by 10 to the minus 2 is going to be something a little bit greater than 1 times 10 to the minus 5. So here's what we'll get. 2.5 10 to the fifth seconds times, and if you divide out 5.8 divided by 5, that's going to turn out to be 1.16. This will come out to be times 1.16 10 to the minus 5. Okay? The minus 5 and the plus 5 cancel. 1.16 times 2.5 comes out to be something like 3 arc seconds. And that's not very different from the sharpest thing that the atmosphere will permit you to see. Typically we could look through in a seacoast town, you might see something, the sharpness might be about 2 to 3 arc seconds. So the official resolving power of this telescope, the diffraction limit, is just about what the atmosphere permits you to see, and turns out to be about 3 arc seconds.